Dear students, now let us see the concept of angular impulse. So this angular impulse, it is analogous to linear impulse. So what is meant by linear impulse? Impulse in the case of a straight line motion is called as linear impulse, which we have already discussed previously. Let us try to revise this one again. So I is equals to F into T. So if a force is applied for a very small interval of time, then the product of this force and time is called as impulse. So this impulse, it changes the linear momentum of the body, or we can write mv minus mu, or I can write delta into p. So that is the amount of change in linear momentum of a body is also called as impulse. So this is the equation I can write if a force is a constant. For example, if a force is not a constant, then same equation I can write like this also. So I is equals to integration of f into dt, limits are applied from t1 to t2. So this is also the equation for impulse. In the case that if a force applied is not a constant, then this is also responsible for a change in linear momentum of the body of the center of mass of this body. So same concept we can apply in rotational motion also. So linear impulse I will indicate by I, and angular impulse we will indicate by J. So J is equals to, instead of F I can write a torque here, so tau into T. So this becomes our equation for angular impulse. So linear impulse changes linear momentum of a body, so angular impulse will change angular momentum of a body, which can I write it as L final minus L initial, or also I can write it as I omega minus I omega naught, where omega is the final angular velocity, omega naught is the initial angular velocity, or I can write delta L also. And this is again the equation for angular impulse if torque is a constant. For example, if torque is not a constant and if it is a variable, then I can write J is equals to integration of tau into dt, and again limits are applied from t1 to t2. So this is also equals to the change in angular momentum of the body about the center of mass. So therefore I can write angular impulse changes angular momentum of a body about the center of mass. Okay, so previously we have studied that I is equals to F into T. So this is exactly like area is equals to length into breadth. So therefore, if I draw a graph of force and time, for example, if graph is like this, then area under this force and time graph, this area it should give the linear impulse of the body. So I is equals to area under ft graph. Same concept I can write here also. Similarly, if I draw a graph between torque and time, so this is the torque applied and this is the time, and for example if graph is like this, then definitely the area under this torque and time graph, this area should provide angular impulse of the body. So let us try to understand this concept by considering some examples. Dear students, now let us see this question. A uniform disk of mass m and radius r is smoothly pivoted at the center. From a string wrapped around the disk hangs a particle of mass small m. If the system is released from rest, find angular speed of the disk by using the concept of angular momentum. So angular momentum we can always calculate in two methods. So by using law of conservation of energy also we can calculate. But here we are trying to calculate angular velocity by using the concept of angular impulse. So first already we have discussed about angular impulse. J is equals to torque into time is equals to change in angular momentum. So L final minus L initial. So which particle is providing torque here? So weight of this particle mg, so this force is providing torque for this disk. So torque can be written as F into R. So F is mg, so mg into radius. So torque is acting at a radius of R here. So torque is mg into R. So now if I study about initial angular momentum, so here in this system two particles are having angular momentum. One is this particle mass m is also having angular momentum, and this disk is also having some angular momentum. But initial angular momentum, we can say it is 0, because when this particle is about to release, angular velocity of this disk is 0 and linear velocity of this mass is also 0. So total initial angular momentum is 0. Then let us try to calculate final angular momentum after a time of t. So after a time of t, let velocity of particle be v and angular velocity of disk let it be omega. So after a time of t, this particle has reached a velocity of v, and this has a rotational velocity of angular velocity omega. So therefore final angular momentum can be written as angular momentum of disk plus angular momentum of the particle. So angular momentum of a disk is I into omega. So I value is half mr square for a disk, and angular velocity is omega. Angular momentum of the particle is mv into r. From this axis of rotation, it is at a distance of r. So m into v into r. So this L final minus L initial is equals to L final only, because L initial is 0. So therefore I can write half m r square into omega plus m. V is a tangential velocity, and this tangential velocity can be written as omega into r. So omega into r into r. So which is equals to half m r square into omega plus m omega into r square. So this change in angular momentum, this should be equal to the product of torque into time according to the concept of angular impulse. So therefore torque into time, which already we have calculated, is equals to mg into r, and multiplied by time is equals to omega. If I take a common, then it is equals to half mr square plus mr square. So if I multiply total equation by 2 and cancel this r values, then I can write 2 mg into t divided by 2 is getting cancelled. So r, if I take a common, then I will get m plus 2m. So this should be our equation for angular velocity. Of conservation of angular momentum in the case of collisions. So previously we have studied the concept of collisions. Now we will see how we can use the concept of this conservation of angular momentum in the case of oblique collisions. So oblique collisions, let us revise that one. For example, this is a body of mass m traveling with a velocity of v, and this is another mass which is in rest position, and its mass is also m. So after some time they will collide like this. So this is one body, this is another body. So previously this was the velocity direction. So these bodies, they have now two components which already we have discussed. So this velocity vector I can split into two components. One velocity along common normal and one velocity along common tangent. So this will be the direction of common tangent here. So this velocity vector always I can split into two components. So this is one velocity, this is another velocity. So if this is v and if this is theta, then this is v cos theta and this is v sin theta. So v cos theta is the velocity along common normal, and v sin theta is the velocity along common tangent. So if collision is perfectly elastic and masses are equal, so if it is a perfectly elastic collision and masses are equal, then already we have studied that. So this v cos theta will be exchanged in the sense, so this velocity vector which was previously having two components, v cos theta and v sin theta, now this body it starts traveling after collision only with the velocity of v sin theta, because v cos theta has vanished, v cos theta of first body has become 0, and this v cos theta will be taken by the second body. So first body travels now after collision with the velocity of v sin theta, and second body it travels with the velocity of v cos theta. This is what we have studied. For example, if two bodies, if they are colliding head on and if their masses are equal, if this is traveling with the velocity of v and this is in rest position, then after collision first body will go into rest position and second body will take the velocity of first body and it will continue motion. So here exchange of velocities is in the direction of common normal. Here also same concept. So this is the common normal. So in this direction velocities will be exchanged, and this v sin theta will not change for the first body. So this is what we have discussed previously. Now we will consider, for example, one body is a very big body and another one is a very small body. This is small m and this is capital M, and now it is traveling with the velocity of v. So if it travels with the velocity of v and if it collides, because this is a very small body, it almost loses its velocity in the direction of common normal, and now it has only velocity along common tangent. So if this velocity is v1, then I can say this body, this bigger body, it travels with a velocity of v2. So here also I can say that velocity along common tangent is v1 and velocity along common normal is v2. So this smaller body, it has velocity only along common tangent, and bigger body has started to travel with a velocity of common v2 in the direction of common normal. So previously, if it is an elastic collision and if masses are equal, then this angle should be 90 degrees. That also we have studied. So in this condition also almost the same condition will be satisfied, because one particle is a very small particle, so it almost completely loses its velocity in the direction of common normal, and it has velocity only along common tangent. So now if I study about the properties of this type of collision, now let us see what are the properties in this type of collision if one mass is a very small mass and the second mass is a very, very big mass. So here I can say, because this is an elastic collision, total energy should be always conserved. So total energy must be conserved, because in the case of elastic collision, total kinetic energy is always conserved and total energy is already conserved. So I can write here also, total kinetic energy is also conserved. Okay. So, but if I study about this single particle, then I can say that its kinetic energy of a particle, kinetic energy of the particle is not conserved, because as we are seeing that this bigger mass, it will give some impulse on this smaller body, so definitely its velocity has changed. If its velocity has changed, definitely its kinetic energy is not conserved. So next I can write, so linear momentum of a single particle is also not conserved. So I can write linear momentum of particle is also not conserved, because as velocity is changing, definitely linear momentum also should change. So, but if I consider angular momentum immediately after collision, then angular momentum is conserved, because on this particle, this bigger sphere is not giving any angular impulse. So definitely I can say immediately after collision, immediately after collision, angular momentum is conserved, because sphere, that is this bigger ball, sphere is not giving any angular impulse. So already we have studied that angular momentum of a body can change only if you can give angular impulse. So in this collision, this bigger sphere is not giving any angular impulse to this small mass. So therefore immediately after collision, its angular momentum should remain constant. So this is a condition where we are saying that linear momentum of a particle is not conserved, but definitely angular momentum is definitely conserved. So now let us try to study these collision conditions in two types of cases. For example, if I study case number 1. So what is case number 1? Case number 1 is if axis of rotation is fixed. If axis of rotation is fixed. So that is a body after collision, it is revolving around a fixed axis. In this condition, let us see what are the considerations we can use. So here we considered that the conservation of angular momentum about the axis of rotation. So first of all we will write equation, or we will consider conservation of angular momentum about the axis of rotation. About the axis of rotation. So because about the axis of rotation, definitely we can consider the conservation of angular momentum. And second one is, so as body has a fixed axis, as it has a fixed axis, axis also provides external force. So for example, if this is the body and this is the axis of rotation, so if I apply force here, or if a small mass is coming and colliding this one, then if there is no axis of rotation, then this body should undergo translatory motion as well as rotatory motion. But this translatory motion is opposed by this axis of rotation. So therefore I can say if a body has a fixed axis, axis also provides some external force. So therefore equation of conservation of linear momentum, conservation of linear momentum is not valid. So when axis of rotation is fixed, then we can write the angular momentum conservation about the axis of rotation. But here as axis is also providing some external force, so linear momentum equation we cannot write for this body. Similarly, if necessary, we use the equations of coefficient of restitution and law of conservation of energy. Okay, so these are the conditions if axis of rotation is fixed. Now I will write the second condition, that is case number 2. So case number 2 is if axis of rotation is not fixed. If axis of rotation is not fixed. So if axis of rotation is not fixed, then definitely we can use the law of conservation of angular momentum and law of conservation of linear momentum. So both these equations I can use if axis of rotation is not fixed. Similarly, I can use the law of conservation of energy if it is required. Law of conservation of energy also I can use. Similarly, I can use the equation of coefficient of restitution. Equation of coefficient of restitution. So these are the considerations which I have to use depending on whether the axis of rotation is fixed or axis of rotation is not fixed. So axis of rotation is not fixed in the sense body can undergo translatory as well as rotatory motions. So let us try to understand some concepts, some problems based on this discussion. Dear students, now let us see this question. A sphere of mass m and radius r rolls without slipping on the horizontal surface with speed v. So during its motion, it encounters a fixed rectangular block of height h is equals to r by 4. If the collision is elastic, find the angular speed of the sphere immediately after collision, and the body rolls without slipping. So this is the given figure. Let us try to draw a bigger figure of this one. So this is the sphere which is having a radius of small r, and here there is a fixed block whose height, this height is equals to r by 4, where r is the radius of this sphere, and this sphere, it is traveling with a velocity of v. Then after some time, this sphere, it comes and collides with this block which is fixed here, and it starts rotating around this axis. So this point, it will become the axis of rotation. So if I draw that picture also, then I can draw like this. So this is the sphere, and this is the fixed block. So now rotation starts around this point. So velocity direction, that is velocity after collision, I can write this is omega v dash, and its angular velocity has also changed. Now I can call its angular velocity as omega dash, if previously its angular velocity is omega. Now if I study about the axis of rotation, so this becomes my temporary axis of rotation. So on this axis, how many forces are showing their torque here? One force is mg. So this mg will produce a torque around this point. But because this is a collision, the impulsive forces are very large when compared to weight of this body. So therefore I can write impulsive forces are very large when compared to weight of body, because we know impulse is equals to F into T. So this collision is happening for a very, very small interval of time. So therefore the impulsive force generated will be very large when compared to weight of this body, or I can say that torque produced due to weight of this body is 0. Now on the axis of rotation, total torque acting is 0. So total or net torque acting about the axis of rotation will become 0. So if net torque acting is 0, then I can say dl by dt is also 0, or I can write L is a constant, or I can say angular momentum should be constant. Now for this sphere, angular momentum is because of two motions. Because of translatory motion also it has angular momentum, and due to rotatory motion also it has some angular momentum. And as angular momentum is conserved, so therefore I can write L translational initial plus L rotational initial should be equal to L translational final plus L rotational final. So because of translatory motion, how much velocity, how much angular momentum it has. So this is a velocity of v at an axis of, so I want this distance, which is the perpendicular distance from the axis of rotation, and this distance is nothing but r minus h. So therefore translatory motion due to angular momentum due to translatory motion can be written as mv into r minus h, plus now angular momentum due to rotational motion can be written as I into omega. Omega can be written as again v by r, and moment of inertia for a solid sphere is 2 by 5 mr square. So I will write 2 by 5 mr square into, instead of omega I will write v by r. So this is the initial angular momentum. So final angular momentum I can write like this, mv dash into, now this body is rotating around this axis, and perpendicular distance from this axis of rotation is r itself. So plus 2 by 5 mr square into, again instead of angular velocity I can write v dash divided by r. So if I manipulate this equation, then the equation which I will get is, so 3 by 4 mvr plus 2 by 5 mvr is equals to 7 by 5 mv dash into r. So further if I simplify this one, then I should get, so 23 by 20 mvr is equals to 7 by 5 mv dash into r. So from this if I calculate v dash, then it should be equal to 23 by 28 v. So therefore we got this velocity. So once we get velocity, we can very easily calculate angular velocity, which is omega dash. So omega dash is equals to v dash divided by r, which is equals to 23 v divided by 28 into r. So this is our answer for final angular velocity after the collision. Now let us see this question. A thin uniform rod of mass m and length L is lying on a smooth horizontal floor. So let us draw this diagram. So this is a rod of mass m and length L. So it is lying on a horizontal floor. So it is struck by a force normally at one end. So by using some force we are striking this rod at one end. So and the time of application of force is very small, which is equals to t naught. So this time is applied for a time of t naught. Then find the distance traveled by the rod by the time it is turned by an angle of pi by 2. So therefore by the time this rod rotates by an angle of pi by 2, we are supposed to find out the linear distance traveled by the rod. First of all, if I apply force here, why does this rod travel? Why does this rod rotate? So if a force is applied on the center of mass, then definitely there cannot be any rotational motion. but force is not applied on the center of mass, so definitely there will be translational motion as well as rotational motion also. So therefore, if I consider the concept of linear impulse, linear impulse can be written as I is equals to F into T naught. It provides the change in linear momentum. So P final minus P initial. P initial is 0 because this rod was in rest position. So therefore, F into T naught is equals to P final is M into it gains a velocity of V. So this is our equation number 1. So this is the linear impulse which is generated, force into time. So it produces a linear momentum of mass into velocity. The same force, it produces angular impulse also about the center of mass. So if I study about angular impulse, then angular impulse J can be written as torque into time. So torque can be written as F into R into T. So force applied is F, and from the position of the axis of this rod, or you can call center of mass of this rod, this is at a distance of L by 2 into time of application of force is T naught. So this is the angular impulse which is generated. So angular impulse, it changes the angular momentum of the rod. So therefore I can write L final minus L initial. So again in this condition, L initial is 0 because initially rod was in rest position. So therefore I can write J is equals to F into L by 2 into T naught, and angular momentum of this rod is I into omega. So I value is ml square by 12 into omega. So this becomes our equation number 2. So if I divide these two equations, then force and this T naught get cancelled, then I will get equation for omega. So the equation for omega, by dividing equation 2 and 1, I will get equation like this. So F into L by 2 into T naught divided by F into T naught is equals to ml square by 12 into omega divided by m into v. So m, f, t naught, l and square, they get cancelled. So 2 1s are 2 6 are. So therefore final angular velocity which I get is 6v divided by L. So this rod starts rotation with this much of angular velocity after this rod is struck by a force of F. Now he is saying by the time it completes an angle of pi by 2. So we know angular velocity is equals to theta by t, that is angular displacement by time taken is nothing but angular velocity. So angular displacement is pi by 2 divided by time. So therefore omega is equals to pi by 2t. So this is the angular velocity of the rod. So from this I can calculate time taken for this rotation. So time is equals to pi by 2 into omega, and omega value is 6v divided by L. So therefore I can write T is equals to pi by 2 into 6v into L. So therefore pi L divided by 12 into V. So in this time the rod rotates by an angle of pi by 2. So by the same time this rod also travels in translational motion, that is in straight line motion also. For that one, the equation of displacement, I can write displacement is equals to velocity into time. So therefore displacement is equals to velocity into, and time taken already we have derived, which is equals to pi L divided by 12 into V. So V and V gets cancelled. So my answer is pi L divided by 12. So this will be the displacement of the rod by the rod completes an angle of rotation of 90 degrees. Dear students, now let us see this question. A uniform rod of length L and mass m lies on a smooth horizontal plane. A particle of mass m moving with a speed at a speed v perpendicular to the length of the rod strikes it at a distance of L by 6 from the center and stops. Then find the velocity of center of mass of the rod, and then second question is angular velocity of the rod. just after collision about its center. So let us try to represent this question in the form of a diagram. So this is a uniform rod whose length is L and mass is capital M, and it is present on a smooth horizontal surface. So this rod is horizontal, and from the center at a distance of L by 6, a particle of mass M, it is coming with a velocity of v. It is striking this rod at a distance of L by 6 from the center, and immediately this small mass is going into rest position. So then let us see how we can calculate the first question. So what is the velocity of center of mass of the rod? So in this condition, so this is a condition of where body is not fixed around any axis. So here I can say this is a condition of axis is not fixed. Axis of rotation is not fixed. So if axis of rotation is not fixed, axis cannot apply any force on this rod. So therefore I can say total external force acting on this total system is 0. If total external force acting is 0, then momentum should be a constant. Which momentum? Linear momentum should be a constant. So therefore I can write m1 v1 is equals to m2 v2. M1 is mass of this small particle m, and it is traveling with a velocity of v, and m2 is the mass of the bigger rod, which is m, capital M, and final velocity of this one we don't know, so v2. So v2 can be written as velocity of center of mass also. So vcm is equals to m into v divided by capital M. So this is the velocity of center of mass of this rod. So if axis is not fixed, definitely I can apply the law of conservation of linear momentum. Now let us see the second question. So what is the angular velocity of the rod after collision about its center? So angular velocity very easily I can consider by using the law of conservation of angular momentum also, because on this total system torque acting is 0. If torque acting is 0, then dl by dt is also 0. That is differentiation of angular momentum with respect to time is also 0. It means L is a constant. So therefore L initial should be equal to L final. Initially only this particle, it was having angular momentum about its center, and this type of angular momentum is a translational angular momentum, so which we can write as m into v into, now from the center of this rod it is at a distance of L by 6, so L by 6, and final angular momentum, only rod is having angular momentum. Around its center of mass it was traveling, it rotates with an angular velocity of omega. So angular momentum about the center can be written as I center of mass into omega. So I center of mass of a rod is, we know it is ml square divided by 12 multiplied by omega. So therefore mvl by 6 is equals to ml square divided by 12 into omega. So 6 1s are 6 2s are, L and square get cancelled. So omega is equals to 2mv divided by capital M into L. So this will be the angular velocity of the rod. This we have calculated by considering the law of conservation of angular momentum. Now in the same problem, now after this particle collides this rod, previously we have considered a situation that after collision this mass will go into rest position. So instead of this mass going into rest position, if it is sticking with this rod and rotating along with this rod and translating along with this rod, then what are the conditions for the same questions which were asked in the previous question? So after collision, if it is striking, if it is attaching with this rod, then I want to calculate the velocity of center of mass of the rod and angular velocity of the rod just after collision about its center. So let us see how we can do this problem. So here the given condition is like this. So this is the rod of mass m and length L. So this is the center. So at a distance of L by 6, so this particle of mass m, it is striking with a velocity of v, and after striking it is getting attached to this rod and it is moving along with this rod. So as again there is no axis of rotation is not fixed in this condition. So definitely I can use the law of conservation of linear momentum. So linear momentum says that total initial momentum is equals to total final momentum. So initially only this particle was having linear momentum, which is equals to m into v. Now after collision, this mass is getting attached to this bigger rod. So now the total mass is m plus m, and this rod is having a center of mass velocity which is called vcm. So therefore I can write velocity of center of mass is equals to m into v divided by m plus m. So this is the velocity of the center of mass of the rod with which it travels translationally. Now the second question is also present. What is the second question? Angular velocity of rod just after collision about its center. So in this condition also I can use the law of conservation of angular. So now after collision, this mass is again attaching to the rod here. So therefore definitely I can use the law of conservation of angular momentum, because the net torque acting on this system is 0. For the total system I can write torque acting is 0. So therefore dl by dt also should be equal to 0. So therefore L should be a constant. So initially only this particle was having angular momentum, so which can be written as about the center of mass of this rod, angular momentum is m into v into L by 6. Now after collision, this mass is getting attached with this rod. So therefore now this rod as well as this particle, both of them are traveling or rotating around this center of mass. So total moment of inertia can be written as ml square by 12, which is moment of inertia of the rod, plus mr square, and r value is L by 6. So m into L by 6 whole square, so multiplied by omega. So this is the moment of inertia of the rod, and this is the moment of inertia of the single particle which is at a distance of L by 6 from the axis of rotation. So therefore I can write mvl divided by 6 is equals to ml square by 12 plus ml square divided by 36 into omega. So therefore mvl divided by 6 can be written as, now here if I take LCM, then that is 36, 3ml square plus ml square into omega. So 1s are 6 are. So therefore 6mv and L is equals to 3ml square plus ml square into omega. So L and square of L get cancelled. So 6mv divided by L, if I take common, then 3m plus m is equals to omega. So this is the angular velocity of the rod. Dear students, now let us see this question. A uniform rod of mass m and length L lies on a frictionless surface which is horizontal. A particle of mass m moving with a speed v0 perpendicular to the length of the rod strikes the end of the rod and sticks with it. Find the velocity of center of mass and angular velocity about the center of mass we are supposed to find out. So let us see how we can draw a diagram of this one. So this is a rod of mass m and length is L. So now where this particle is striking, moving with the speed of perpendicular to the end of the rod, strikes the end of the rod and sticks with it. So there is one more particle whose mass is also capital M. So it is striking with a velocity of v0. So after striking, it is sticking with this rod. Then we are supposed to find out velocity of center of mass and angular velocity. So velocity of center of mass very easily we can calculate, because on the total system the force acting is 0, external force is 0. If external force is 0, dp by dt is also 0, change of linear momentum. So therefore I can say P is a constant. So therefore total initial momentum is equals to total final linear momentum. So initially only this particle was having momentum, so m into v0. So finally this mass and this mass, both of them, they are sticking together. So total m plus m and their center of mass is traveling with the velocity of vcm. So therefore I can write velocity of center of mass can be written as, so m into v naught divided by 2m. So m gets cancelled, so v naught divided by 2. So therefore velocity of center of mass of the system, it is traveling with the velocity of v naught divided by 2. So now the question is, we have second question also. So we are supposed to find out angular velocity about the center of mass. So first of all, after striking, now this is the condition. So this is a mass of capital M, and here there is one more mass which is also capital M. So first of all, we will try to find out the position of center of mass. So x center of mass is equals to, we know m1 x1 plus m2 x2 divided by m1 plus m2. So consider this is my x-axis and this is my origin. So we are trying to calculate the center of mass from this position, because already we have studied that for calculating center of mass, definitely there should be some point of reference. So from this point, this capital M is present at the origin itself, so its position will become 0. So therefore I can write x center of mass is equals to m into 0 plus, now this capital M, for this rod, its center of mass lies at a distance of L by 2. So 0 plus m into L by 2 divided by m1 plus m1 is 2m. So therefore x center of mass is equals to ml divided by 4 ml divided by 2m. 2m, this is one more 2 is there, so therefore m and m gets cancelled. So therefore x center of mass is equals to L by 4. So therefore center of mass of this total system, it is lying somewhere here at a distance of L by 4. Now we are supposed to find out angular velocity, and this is again a system of axis is not fixed. So this is a condition where axis is not fixed. If axis is not fixed, definitely we can say force exerted by the axis will not be present. So therefore definitely we can use the law of conservation of angular momentum. But this law of conservation of angular momentum, we are supposed to find out about the center of mass. So therefore initially this particle is having a mass of m and velocity of v naught, and from the center of mass it is at a distance of L by 4. So therefore its angular momentum will become, so m into v naught into L by 4. So this is the initial angular momentum. So final angular momentum I can write like this. So moment of inertia about the center of mass multiplied by angular velocity. Now what about moment of inertia about the center of mass? About the center of mass, two particles are having moment of inertia. So one is the rod itself, whose mass is concentrated at a distance of L by 2. And there is one more particle, this point mass, which is present at a distance of L by 4. So therefore, let us see how we can write. So mv naught L by 4 is equals to, first I will write moment of inertia of the particle, which is at a distance of L by 4. So m into, for a single particle, we know moment of inertia is mr square. So m into L by 4 whole square. Now for moment of inertia of rod. So for the rod, I will use parallel axis theorem, because for the rod around the center of mass, we know moment of inertia is ml square by 12. So ml square divided by 12. But we want axis here, which is at a distance of L by 4. If this distance is L by 4, then this distance is also L by 4. Now I want moment of inertia of the rod around this axis, which is the center of mass. So therefore we can use the parallel axis theorem, which is I center of mass plus md square. So plus m, now what is the distance between these two axes? Distance between these two axes is L by 4 whole square. So multiplied by omega. So this becomes the total moment of inertia of the rod. So therefore mv naught L by 4 is equals to total moment of inertia. If I calculate, it will be equals to 5 by 24 ml square into omega naught. So therefore if I calculate the value of omega, then the answer which I should get is 6v naught divided by 5l. So check this answer. Now let us see this question. So two uniform rods A and B. So this is rod A, this is rod B, each of length 0.6 meter and each of masses 0.01 kg and 0.2 kg are rigidly joined end to end. So the combination is pivoted at the lighter end P as shown. So this is the axis, horizontal axis around which this rod can rotate in a vertical circle, such that it can freely rotate about point P in a vertical plane. A small object of mass 0.05 kg, this object, moving horizontally hits the lower end of the rod and sticks to it. So it is going here, and after collision, it is in perfectly inelastic collision. So it sticks with this combination of rods and it travels along with these rods. What should be the velocity of the object? So this velocity we are supposed to find out so that the system could just be raised to the horizontal position. So previously rod was like this. Now just the rod should become like this about this point of rotation. So then what is the minimum velocity of this mass required so that if it hits at the bottom, then this rod should be able to just go to the horizontal position. So this is my condition. So let us see how we can do this problem. So first of all, this is a condition of fixed axis rotation. So already we have studied that what we should do if axis is fixed and if axis is not fixed here. So this is a condition of fixed axis rotation. So if axis is fixed, then definitely we have to apply the conservation of angular momentum concept only about the point of rotation, or about the axis only we can apply the angular momentum equation, because if I try to apply angular momentum equation other than the point of axis, then axis is also applying some torque on another points. So therefore the torque due to axis also we have to consider. It means angular momentum cannot be conserved because external force is given by the axis in this condition. So angular momentum, I have to write an equation only for only about the axis of rotation itself. So and initially only this mass was having angular momentum, and after this strikes and sticks this one, then this total system also will have an angular momentum. So whose angular momentum initially is equals to angular momentum just after collision. Because after some time this rod, if it has started rotation, then weight of this total components, it starts giving external torque on this total system. So therefore angular momentum is conserved only immediately after collision. So I hope you are understanding what I am saying. So let us try to understand. So therefore angular momentum equation is conserved immediately after collision. Because sometime after the collision, for example, if rod becomes like this, then the total weight of the rod starts acting in downward direction, which will give an external torque on the axis of rotation. So then definitely angular momentum is not conserved. So therefore angular momentum equation can be conserved only immediately after collision. So therefore I can write after immediately after collision, L initial is equals to L final. Initially only this mass was having angular momentum about this axis. So its mass is m and its velocity is v, which I am supposed to find out, and it is hitting at a perpendicular distance of L plus L to L. Length of both the rods are equal, so perpendicular distance will become 2L. So this should be equal to I axis into omega, so which is the angular momentum of the total system about this axis. Now about this axis after collision, how many masses will have angular momentum? So this mass is going and sticking with this one. So this also will have angular momentum about this axis. Similarly, this rod, first rod, whose center of mass is located at a distance of L by 2. So this also has angular momentum about this point. Similarly, for the second rod, its center of mass is present at a distance of L by 2 plus L, so which is equals to 3L by 2. So this distance is L by 2 and this distance is L, so total distance will become 3L by 2. So three masses will have angular momentum about this axis of rotation. So therefore, if I wrote moment of inertia of all these bodies, then this is how I can write. So m into v into 2L is equals to, first of all, if I take this point mass, so for point mass moment of inertia is mr square, so m into, and perpendicular distance from the axis of rotation is 2L, so 2L whole square. Now if I study about the moment of inertia of first rod, so its mass is m1, and for this rod, axis is at the end of the rod, then moment of inertia is ml square divided by 3. Already we know that equation. So m1 into L square divided by 3. Now what about moment of inertia of the second rod? So its mass is m2, and this is the center of mass of this second rod, but axis of rotation is present here. So for a rod, moment of inertia is ml square by 12. So m2 into L square divided by 12. So, but this is the axis only about this point, but my axis of rotation is present at a distance of 3L by 2. So therefore I have to use the parallel axis theorem. So ml square by 12 plus md square. So m2 into, now what is the distance between these two axes? The distance between these two axes is 3L divided by 2. So 3L divided by 2 whole square. This is the total moment of inertia of all the three masses multiplied by omega. So now if I substitute all the numericals which are given, so let us list out what are the numericals which are present. So length of each rod is 0.06 meter. Mass of the single particle is 0.05 kg, and mass of first rod is equals to 0.01 kg. Mass of the second rod is 0.02 kg. So if I substitute all these values here, then omega and v, only these two are the unknown quantities. So if I substitute them, the angular velocity equation which I should get is omega is equals to 0.67 v. So let it be my equation number 1. So it means that after collision, then this total system, it has started rotating with an angular velocity of this much angular velocity, 0.67 into v. Now this total system has a kinetic energy, the sum of translational rotational kinetic energy, which is equal to half I axis into omega square. So this total energy, when it has reached to the horizontal position like this, then this total rotational kinetic energy has converted into total potential energy of the system. So that is, I am using the law of conservation of energy. So we know that total rotational energy is half I axis into omega square. This should be converted into total potential energy of the system. So for example, this mass. So this mass, initially it is at a depth of 2L. Now it will go to a height of 0. If I take this position as my 0 reference position. So, or if I take this as my reference, or this I consider as my 0 potential energy line, then this mass finally, when it rod has become horizontal, this mass has raised to a vertical displacement of 2L. Now what about first rod? Its center of mass is present at a distance of L by 2. So after becoming horizontal, its center of mass position also has shifted by L by 2. Similarly, if you see the second rod, now it is at a depth of 3L by 2. So therefore, when rod becomes horizontal, its center of mass also will rise to a height of 3L divided by 2. So therefore, this is how I can write. So half I axis into omega square is equals to, so I will write potential energy equations for all these bodies. First of all, if I take this point mass, then its height has raised by a distance of 2L. So therefore, its potential energy will be mg into 2L. Now what about the first rod? First rod is having a mass of m1, g, and it has raised to a height of L by 2. So therefore L by 2 is the potential energy. And m2 g into, now it has its center of mass has raised by distance of 3L by 2. So 3L divided by 2. So these are the equations which we got. So I-axis already we have calculated by this method. So if I substitute all these values, then I will get angular velocity, which is the only unknown quantity, which is equals to 4.2 radians per second. So this is my equation number 2. So already here we got equation number 1, and now here we have the equation number 2. So just equate both of them. So 4.2 is equals to 0.67 into V. So therefore V is equals to 4.2 divided by 0.67, which is equals to 6.3 meters per second. It means this particle should strike this bottommost point of this combination with a minimum velocity of 6.3 meters per second. Then the rod can it can become horizontal.